Hello, I'm Justin Mickling, and I'm here today to talk about IoT security at scale and share some of the experiences Rigado has had with managing end-to-end security for commercial IoT gateways. Level set here, the topics I'm going to talk about are a quick context on Rigado and our focus in IoT, and give you our point of view on commercial IoT, as well as do a deep dive into many of the threats and how we mitigate those with our IoT gateways. Simply put, Rigado's focus is to provide edge connectivity and computing to teams delivering large-scale commercial IoT solutions, allowing them to reduce complexity, cost, and risk. And we've done that for 7 years with over 300 clients and managing or delivering about 5 million devices. In that time, our focus has gone from a lot of consumer BLE mostly devices, things like bike computers, fitness trackers, all the way up to even working with action cameras. And we've transitioned that to working a lot more in commercial IoT, where the needs and the use cases are a lot different. Our product is a edge compute and connectivity solution, so a gateway that has a managing or monitoring and orchestration tool and security updates. So a little bit of context into why we want to talk about this in terms of commercial IoT. When we look at consumer IoT, it's too simple. We can't rely on people's phones all the time. And if you look at industrial IoT, it's too complex and expensive. It doesn't make sense to put a $2,000 server gateway in every classroom or every boardroom. So what we find in commercial is that they have the right mix of connectivity and computing with the scalability and security required for commercial IoT. What are those commercial IoT applications? They range from things like smart buildings, connected lighting, those sort of solutions that are helping get operational efficiency and lower maybe the cost of your HVAC system. Asset tracking and location services. A lot of our customers are trying to find that crash cart in the hospital, save time by not having downtime with those tools. There's a lot of sensoring and monitoring for being able to report usage, or if a consumable is used up on an assembly line, being able to detect that and have reordering done automatically. And then especially things like guest experiences. And we see that in all kinds of IoT segments, but mostly in retail, hospitality, transportation, healthcare, these sort of places where there are typically large office buildings, a lot of low-power devices distributed within them to collect all this data and then send it to the cloud. What we see in these commercial IoT opportunities, like asset tracking, connected retail, and smart buildings, that are using a lot of short-range wireless IoT or BLE Zigbee thread, they need to be able to have all that data crunched at the edge. But they require, what essentially a different approach to the edge infrastructure. Especially around having a lot of different options for wireless, being able to run different workloads there to compute the sensor data and turn it into something that is much smaller and more meaningful before sending to the cloud. And then especially around security. And that all needs to be done at scale, where we're often seeing operations of thousands to tens of thousands of units. When we think about that, the important recipe or topology that we see is a lot of IoT devices, maybe occupancy sensors for conference rooms, lighting controls, things like pallets that have asset tags on them so they can be tracked. And we want to get all of that data up into the cloud. The missing link for that is essentially the IoT gateway, where all of that wireless connectivity, whether it's Zigbee or Thread, or in our case, mostly Bluetooth, Bluetooth 5, that's all brought together in the gateway, where there's connectivity management, the ability to integrate with all those different cloud services, and then be able to get to manage the security as well. If we take a deeper look into our perspective and what those needs are on the gateway, the connecting to the devices, we've learned that there's a lot of different options for connectivity, and getting APIs available for standardizing some of those things like Eddystone beacons, iBeacons, Bluetooth mesh helps with developers, making it a lot easier for them to get connected. And then we've got edge applications. And the important thing here is, in the previous slide, I mentioned maybe 3 or 4 different types of devices. There are often heterogeneous mixtures of maybe a lighting system and a pallet tracking system used in the same warehouse. So these edge devices need to be able to run multiple different kinds of applications for multiple different vendors in order to support all of the IoT needs of the smart buildings or connected warehouses of the future. And we see a lot of that happens in simpler languages like Node.js or Python, but there's still a lot of C++ and now actually a lot of Go applications being written around that edge framework. And all of this obviously needs to connect to the cloud through connectivity like Ethernet with PoE, Wi-Fi, or cellular connectivity. All that is really what the gateway does. It's how it gets data to the cloud. It's what it connects to, and that's directly meeting the needs of a lot of our customers' applications. But what we found from talking to hundreds of customers is that there's also a need for care and feeding for the gateway itself. The gateway needs to have performance monitoring. All of those applications that are being written for it need to have a simple way to manage, to push updates, to deploy configurations. We've learned that everybody wants to follow the same sort of cloud ideas of DevOps for continuous integration and continuous deployment. And that for the most part, while developers are focusing on building their application that is gathering the guest experience data, they aren't spending time worried about the security patches. So the system that the gateway provides needs to include some sort of regular security patches and a automatic security infrastructure. That's what I want to dive into deeper in the rest of the conversation here is about the different threat models that we evaluate when we're talking about IoT gateways and IoT devices, and some of the methods that are employed to prevent or to mitigate those issues. First, I like to think about the data centers when I think about IoT security and think about public cloud as a reference. These public clouds and data centers have enough resources to use VMs or containers to separate workloads and reduce risk. They typically have really good physical security, key card access, limited personnel can actually get into the data center. Their networks are very good in terms of either software-defined networking, providing limited access to different hosts or ports. There's a ton of performance monitoring, anomaly detection tools. In essence, when working in a data center or a public cloud, you're trusting the cloud provider to solve a whole lot of these security problems. And in fact, a lot of people, move to the cloud for that reason, but often kind of assume that it's all there. If we compare that with something like a hotel room, where deploying IoT devices into hundreds or thousands of rooms drives down the budget for processor and RAM on these devices, while still needing to support multiple different simultaneous applications like guest experiences, monitoring the minibar, integrating with HVAC, or controlling the lighting, there's a lot of different needs in an entirely different environment that these IoT devices operate in. And another important note in the hotel room here, there's no physical access control unless you actually hide that gateway in the ceiling or behind a wall or inside something. So there are vastly different environments between something like a public cloud data center and the actual rooms and warehouses, conference rooms, commercial buildings where IoT devices are typically deployed. And there's many different kinds of threats that brings up. There's some similar threats, but even then there's different ways that those threats need to be handled due to the system constraints of maybe a very small amount of RAM or processor speed. So if we take a look and just list a couple different classes or types of security threats at the IoT edge devices, the first one here is kind of a play on the noisy neighbor. We all know that in cloud, there's a lot of different devices running together on a single piece of hardware. We need to provide the same solution in IoT, where we're multi-tenant, but we've got a limited resource system, so we need a low overhead way to do that. There are a couple physical attacks, since that gateway is, or that IoT device is accessible to somebody who can actually put their hands on it. So somebody could tamper with that, change the behavior of the application. They could crack open the device and actually steal some of the information from the storage inside. Maybe that's API keys, maybe that's other IP that's contained inside. And then, you know, like a lot of the cloud applications, we always have to worry about, you know, exploiting the software bugs that are on these devices to create some sort of remote execution. We've heard a lot of stories about botnets and other IoT devices turning into some, you know, a vantage point for attackers to either, you know, denial of service attacks or mine cryptocurrency or a lot of different ways that attackers might want to take advantage of IoT devices. So I first dive into the multi-tenancy situation, where that threat is really that there's other software and applications on the IoT device. And really these problems have been solved in the cloud and in VMs with containers. But on small resource limited IoT devices, the overhead of running a VM is essentially untenable. Even using containers like LXD drives up memory and CPU usage while adding lots of networking complexity and with like things like bridges or VLANs. And meanwhile, you know, the IoT applications need to interact with non-network interfaces like BLE or serial and need really granular permissions on that. So we've picked snaps for our application confinement to solve these problems because they limit app permissions using AppArmor, seccomp, cgroups, and namespaces, but otherwise behaves like running an application on a Ubuntu system. It's simple for our developers to be able to think in that way. The confinement keeps the OS files safe from the application. It runs as, even though it runs the daemons as root, it doesn't give access to modify things like the etc directory or any of the kernel or any other file systems that are outside of the application. It defaults to limiting access. You know, for example, you can allow access to the dbus interface to talk to BlueZ for Bluetooth, but at the same time disallow access to manage Wi-Fi configuration over this same dbus interface. And we picked it because snaps also keep everything needed for running the application together. So the libraries, the runtimes, all of that's together, which makes those snaps easier to manage and update. With the confinement limiting access, capturing and reporting security events are critical for security at scale. Imagine for whatever reason that app is compromised, reporting that it is trying to, even if it's failing, if it's trying to access privileged paths or resources on the IoT device, getting that policy violation will essentially allow you to do early detection and remediation of any issues. And you can only do that if you have strong confinement and strong access controls and granular permissions on these devices. So the reasons for confinement really aren't different than the reasons for containers in the cloud. You can have a predictable, repeatable, and immutable infrastructure, but on these edge devices where resources are limited, we need a slightly different mechanism that has much lower overhead. Another one of the kind of classes of threats that are important to consider when designing an IoT device is what kind of physical attacks can actually be brought on that device. An important one is tampering with the device, and essentially it's about changing behavior. A bad actor could take the physical device, modify the code that's running on it so that it might act as man in the middle in some way. You know, imagine a system that's checking for usage and sending that information for billing purposes. If an attacker could get access and modify the code, they could change the amount that's reported, or they could do other things. They might decide to siphon off personal data and hold that for ransom. They might be able to mine cryptocurrency using the resources that you have in these IoT devices. So it's important that there are mechanisms in place that prevent physical attacks from changing the behavior of these IoT devices. When somebody takes apart one of these IoT devices, they should not be able to plug in a serial cable to a header on the PCB and have root access. I've seen this in several production commercial devices, and it always amazes me. So my first checkbox here is make sure there's no open debug console on the device. Very, very important. And then if there is a terminal, you know, often there's good reason to have a serial interface on the device to do debug. Don't put a username and password combination on that uses defaults. That's probably one of the biggest contributors to the IoT botnets that are out there with user devices. It's better to have a managed system delivering configuration remotely than having kind of a default username and password that users need to change when they install. My experience is that hardly ever happens. Now, if the attack using these physical attacks is to actually change the behavior of an application, one way to combat that is to make sure that the app can't be changed. When we use snaps, those are essentially a read-only file system. So that prevents someone from being able to tamper with the code that's on a device and instead would have to replace the entire snap. Security is built in layers. So let's say we don't allow, even if we don't allow console access, we still want to prevent something like an attacker from being able to replace an authentic snap with something that's loaded with malware. Fortunately, Ubuntu Core has a strong trust model that uses SHA-3 signatures to validate OS and applications as they're installed. So verifying the application is really, from the author, boils down to having a signature that the system can verify. It does that by holding a copy of the public key and then making sure those match. And there's a whole chain of verifying that public key is in fact signed. And if we follow that signature path all the way back, eventually we end up at the kernel, and we want to make sure that the kernel is in fact verified before it's run. And the mechanism that we do that on our IoT gateways is to actually use secure boot. How does secure boot work? Deep in the processor, there is a first stage bootloader with a set of fuses that are permanently burned with a public key. That public key is for verifying the second stage bootloader. So what the system does is takes a first stage, loads that second stage from the external flash and computes its signature, and then compares that against the public key before starting execution. If that succeeds, the second stage will do the same when loading the kernel from external flash and continues all the way up to the apps. So if we go back to our example, if someone takes the Cascade gateway off the wall and tries to tamper with the files in the flash chip so they can introduce new behavior, the secure boot process will simply prevent the system from booting if those changes were made all the way down into any of these layers of the OS. There's a lot of keys here, and so it's kind of important to note that actually managing all these is fairly complex. Fortunately, Canonical maintains the kernel signing keys, so that is handled through a workflow and a process that Canonical maintains. Then Rigado takes that public key and bakes it into our second stage bootloader, and we have workflows to sign that second stage and protect our keys. Then when that happens, only assets that are actually transferred to the factory where everything is loaded essentially has public information in it. Since setting up those workflows is non-trivial, many good intentioned IoT projects skip over setting them up correctly, and doing that really jeopardizes the entire security of an IoT process, because secure boot is the root of trust for any commercial IoT security at scale. Since that's so important, Rigado's decided that we're going to do that for every one of the gateways that we deploy by configuring them in the factory with the secure boot process. Another one of the threats that we need to look at when we're talking about IoT devices that could have physical attacks is actually protecting the IP, the intellectual property, and any of the assets like API keys or configuration that actually live on that device at the edge. Essentially, gateways and applications need those credentials to start conversations up with the cloud and down to devices, but if somebody can do something like on a Raspberry Pi where they pull out a micro SD card and can put it into their computer, they could browse through the files that are on that file system as easily as looking at the pictures from their summer vacation coming from a digital camera. When the application that is being written here is in something like Python or Node.js or Java, interpreted languages that are all written in plain text, it's quite a vulnerability to have your precious IP there at the edge. Now, when delivering an application, a lot of times it's tempting to put something like what I've shown here as an access token directly in the code. But when we look at keeping IoT security at the edge, we definitely need to consider not putting those credentials directly in the app code, and instead using a service or something like a secrets management tool to deliver those secrets to the device when it's running, instead of passing it through an entire CI/CD pipeline where there's a lot more exposure. So just a quick note: don't put credentials into the app code itself. And another note on those credentials: they definitely should be unique per device. Same with no default usernames and passwords for the device itself. Even at the application level, it's security best practice to keep each one of the device's credentials unique. In order to keep those credentials unique, assuming there's a mechanism like a secrets management service that can deliver that secret to the device, it still likely needs to be stored on the disk, and when it's stored on the disk, that's still a risk for an attacker to be able to read it out of the flash file system. So we've considered several different mechanisms for encrypting that, and one of them I want to talk a little bit about is providing a set of encryption libraries. The chipsets inside the gateway provide encryption, so we could deliver a set of libraries that each application could utilize to protect sensitive information. But we ultimately didn't decide to do that for two reasons. The first is that might protect something like a credential or a configuration, but it typically doesn't protect the entire application, so that whole entire Python application or Node.js application. And the second reason is introducing something like a library or utility for encryption would require every application to be modified. That kind of friction is the enemy of security when we're talking about building IoT at scale. We want to make it super easy for every one of our customers to migrate their applications to Cascade, meaning if they started doing development on a laptop or a Raspberry Pi, we don't want to introduce okay, now you have to stop and go use the special configuration utility to be able to actually take advantage of encryption on these devices. The way that we really need to solve this problem is to essentially provide encryption for the entire file system, so that it encrypts and protects the entire app, all of the code that's there, all of the configure information that's there, and all the credentials that might be stored alongside them. And the way we do that is actually back to that secure boot process that we showed just a moment ago. And the important part about the secure boot process is that it makes sure that we can trust the software we are running. If we trust the software, then we can give it access to use a secret key that's buried deep inside the processor. So again, in this case, when the second stage bootloader is authenticated, there is a crypto key that can be passed into the kernel so that the whole entire encrypted file system can be unlocked and used. This is a little bit different than what you might see. I mean, encrypted file systems exist in Ubuntu, have been for a while, but a lot of those systems depend on a human entering in a passphrase during boot, or a USB stick being plugged into the device during the boot process. Because we can take advantage of a secure boot, we can actually allow this mechanism to be used in the field without any human interaction. So solving the tampering or changing application issues and solving security for encryption for configuration and credentials, those are really important for devices that have physical access, where an attacker could actually get their hands on them. But those are not the only threats that IoT devices have to stand up against. Most of the previous threats focused on motivated attackers with physical access, but I think the scariest attacker is one who can remotely turn an IoT device into a botnet because of a vulnerability in some sort of software. So if we look at high-profile vulnerabilities over the last couple of years, from Meltdown and Spectre, which may not be as appropriate or applicable to the gateway devices, to things like Heartbleed, Blueborn, attacking the Bluetooth connectivity, or Crack, which really attacked the WPA2 Wi-Fi encryption. There are tons of vulnerabilities that happen every month. I think something like 1,800 new CVEs were filed in June this year. So the most important factor in IoT security at scale is frequent security patches that are automatically applied. That's difficult to do when the system does not have clean separation. But fortunately, with Canonical's Ubuntu Core, the snaps provide a really good clean separation of the OS, the system, and then the applications, so that they can all be updated independently. And in the case of what Rigado and Canonical are doing on our Cascade system, those kernel updates happen on a cadence of about 3 to 4 weeks. Critical patches for something like one of these really high-profile vulnerabilities can actually be delivered faster. And I just can't overstate how important it is to be able to have automatic updating that's independent of the app feature releases. If you think about a team that is working hard, regularly having a feature release or a product team pushing on getting features, layering in and doing hot fixes or special releases during for security issues is not a practice that I think a lot of teams have time for. Finding a mechanism at scale that takes care of that for you can really be important. And what I want to say perhaps last about security and the threats that we face is that no security is perfect. If you've got a vulnerability that is not patched yet, somebody could potentially take advantage of a system or an application remotely. It's not enough to try to just prevent it. We also have to do monitoring. So at scale, having a centralized application performance monitoring can identify issues like this one, where CPU performance was nominal at 10% or less, and then spiked up to 80, 90% for some reason. These sort of anomalies need to be flagged so that any attack that happens can be discovered quickly, and a remediation plan can be developed quickly. And then, in efforts to figure out what's happening here, there's also a need for some sort of centralized logging, so that when you see a big spike in CPU or memory or network bandwidth, or you start having anomalies in which hosts the device is talking to, logging can help you go back, look through what's going on, understand where an issue might have been introduced, and understand the scope of that breach. Remember, security isn't perfect. It's good to have tools that help you deal with issues when they come up. All of this has really influenced how Rigado developed essentially one of the core pillars of our Cascade product, which we call Edge Protect. It involves the mechanisms from the hardware and manufacturing process with Secure Boot, get all the security features enabled in our gateways. It also helps with it influenced our decisions to move with snaps and work with Canonical to have confinement that works on our resource limited systems. And then the partnership also enables us to have really good access to continuous updates for security. These are all the important factors in what we have noticed and how we've mitigated the threats on IoT security at scale. And then finally, I want to say that IoT security at scale is not layered in as an afterthought. It is the foundation, and it's built on a root of trust, and it utilizes confinement, signing, and encryption. And it's an ongoing process with security updates and active monitoring. Ubuntu Core takes a security-first approach, and that is why we've picked it for the foundation of our Cascade platform and the pillar of the background of our Edge Protect feature of Cascade. Now I want to take a moment and see what kind of questions the crowd has for how we mitigate threat issues in IoT security.